I'm going to now explain why the most strange-looking exponent rule is true. I would say this qualifies as the most strange. Maybe you think something else is. But most kids feel like a fractional exponent is a little bizarre, the way it's defined and the way it's used. So I'm going to give you a good understanding of it here. The exponent rule itself says that a to a fraction, where the numerator of the fraction is m and the denominator is n, is equal to the nth root of a to the m. And there's actually a second way to write it, which we'll see as we go along. That's the basic idea. So in part one of this explanation, I showed why this is true. So from part one, we have this, that if you take a to the 1 over n, then that is equal to the nth root of a. And I think a moment's glancing at this shows you that these are very similar looking. But the question is, why do we get this formula when the exponent, or the exponent's numerator isn't 1, when it's m? Why does this happen? The answer to this question, and really the answer to all of the questions about exponent rules, all of them, is really the same in a way. The answer to the question is, if we didn't do this, then our other exponent rules would stop working. And that would be a disaster. We don't want to have our old exponent rules stop working just in certain cases. We need it to always be the case that our exponent rules work seamlessly. So I want you to think about a particular exponent rule right now. In particular, we need this one to keep working. That if you take a to the power of a product, m times n, sorry, not a product. If you take a to the m and you raise it to the n. Now I know I'm using m's and n's in this one and in this one. I don't mean them to be the same. This is no longer a fraction. This is just a to some number raised entirely to the power of n. Then I've showed in another video why this has to be true, that it's equal to a to the m times n. We need this to keep working no matter what. So keep that in mind because it's going to be the key to this. And we also, of course, need this one to keep working. So I'd like you to consider a to the m over n for a minute. I'm going to rewrite m over n itself as a product of two numbers. It is equal to this. Sorry, I'm actually going to write it slightly differently. Excuse me. A to the m times 1 over n. Now I want you to think about that exponent. M times 1 over n. Convince yourself that that is the same as m over n. Might look a little confusing to you, but when you have m, that's really m over 1, and you multiply the numerators and the denominators, you get this. So nothing has changed here. This is all in the exponent. But from this rule, I want you to think about that as being like this. If you have a to a product of numbers, it's supposed to be equal to a to that first number in parentheses to the power of that second number. A to the m to the power of 1 over n. Okay. Well, now think about what this has to be equal to. This is a number to the 1 over n. We said here that if you have some number and you raise it to the 1 over n, that means the nth root of that number. So here I have the nth root of the thing inside the parentheses, which is a to the m. And so that's the explanation. A to the m over n has got to be defined this way so that our exponent rules keep working. It's just about that consistency. The last thing that I want to show you about this is that there's actually a second way to write this that's important to see. You could have written in the same set of steps, you could have done something slightly differently, which I almost started doing a moment ago when I erased. I can write m over n actually as 1 over n times m. That's also equal to m over n. I'm just reversing the order. But when I reverse the order, I actually have a different meaning here when I do this. This is a to the 1 over n to the power of m by applying this rule again to this. And think about what a to the 1 over n is. That's just a straight application of this. It's the nth root of a, that, but it's in parentheses to the power of m. Now notice, this is a different expression than this one. These, therefore, have to be the same. They have to be the same thing. The nth root of a to the m has to be the same as the nth root of a to the power of m. Now, I said I wanted to explain why these rules are true, and I have. This is the answer to our exponent rule, and I've actually just showed you that there's actually a second part to this. It's also the nth root of a to the power of n. But the last thing I want to do is actually address a common problem in a first set of homework problems that you would get related to all of this. Here's an example. Simplify 8 to the power of 2/3. This is a problem you'll see in most algebra classes after an introduction to this exponent rule. And I want you to think about the fact that applying this rule to this means you have options. You can either write this, that it's equal to this thing, or you can write it's equal to this thing. So if you look at that first one that I boxed, then I just write what it says. It says take n, notice it's the denominator. N is the denominator. The n here, the root, is that number down there. It's the third root of. It says 8a to the power of the numerator, so 8 squared. That's the third root of 8 squared, which is the third root of 8, obviously, times 8 is 64. And now what you'd have to do is just sit there thinking, unless you had a calculator and you knew how to do this, but I don't think that most teachers would want you to use a calculator. You have to sit here thinking about what number times itself 3 times is 64, which is a little tricky. It takes a while. That's a big number. I want to show you, and we'll write the answer in a second, maybe you know it, but I want you to notice a second method. So this is method number 1. Method number 2 is actually a little easier in this case. 8 to the 2/3 can also be written according to this rule. Again, the n is the denominator is the index of the root. So I have 3. Index just means this number that goes here. It's the third root of 8. But now it's in parentheses, this whole thing, and it's to the power of that numerator squared. Now the difference here between this one and this one is I'm not going to get 64 here, because I'm supposed to take the third root of 8 first. Now again, this is a thought problem, but it's a simpler thought problem. What's the number that you multiply by itself 3 times to get the number 8? That's what this is. And the answer is 2. 2 times 2 times 2 is 8. And so this is the number 2 squared, which is 4. The answer is 4, which is also the answer to this one, of course. You have to get the same number. But notice how much more tricky it is, or more tedious it is, to actually think about, oh, 4 times 4 is 16 times another 4 is 64. Oh, yeah, it works. That's harder. It's not that much harder, but there are certain problems where one of these methods versus the other is going to be much easier than the other, so you want to be flexible with it. All right. I hope that helps. Good luck with fractional exponents.